All right, Dr. Brown, I'm back. All right, I finished my my generic form for a list of an arbitrary number of primes, n primes, and here it is. And I'll explain the parts to you. And I think because I've already explained how I've derived it, then the parts will make sense. So I'm going to use different colors for the parts. Okay. So the gist of it is the polynomial. Oh, I didn't write p. Big paragraph p of x. Let's do that. Big paragraph p of x is a polynomial that returns primes, consecutive primes, for consecutive integer inputs. Okay. It's composed up of different polynomials. This right here is the first polynomial, this chunk, and here's the second polynomial. And there's going to be n polynomials, so that's why I have dot dot dots all the way down to the nth polynomial, and I'll show you the formula for those in a sec. All right, so let's consider just the first polynomial. The first polynomial is going to have this first part of the polynomial gives the polynomial zeros everywhere except for at x equals 1. Okay? Notice how I have x minus 2, x minus 3, x minus 4, and so on up until x minus n, but I'm missing x minus 1. So it doesn't have a 0 there. But what happens when I evaluate this function at 1? Well, that's a good question. I've divided over here, further to the right, over here in blue, this blue chunk divides the result of the green chunk evaluated at 1. I just have on the denominator 1 minus 2, 1 minus 3, 1 minus 4, 1 minus n minus 1, and then 1 minus n. So the blue and green chunk together, when evaluated at 1, give you a result at 1. So my last step, which I'll put in this color right here, is just to multiply it by my first prime, which in this case is 2. But I just put it as arbitrary. Now let me get rid of that yellow. I don't like that yellow very much. All right, so let me show you, obviously, the next one. This will go pretty quick. Let's take a look at the second polynomial that is part of my sum for big paragraph p of x. So let's do this again. I've got my blue chunk that gives me, or did I do blue, green first? I don't remember. So I've got my blue chunk. Now this time, because this is the second summed polynomial, I am going to have a 0 at x minus 1 right here. But I'm going to skip x minus 2 because I want the polynomial not to have a 0 at x minus 2. I want the polynomial to have a 0 everywhere else, so I continue 3, 4, 5, and so on, x minus n minus 1, and then x minus n. So it has 0 everywhere except at 2. But what happens when I evaluate this function, this polynomial, at 2? That's a great question. Well, I've constructed it in such a way, using this portion, this scalar multiple, so that when the blue and green chunk evaluated at 2 equals 1, I've divided here on the denominator, I've divided by particular integers that is the blue chunk when evaluated at 2. So the blue and green chunk together evaluated at 2 is equal to 1, so the only thing left to do is multiply by p sub 2, which is the second prime, which would be 3. Okay? So pretty much each polynomial has zeros everywhere except for on its index, x, when x is equal to its index. And when x does equal its index, it just spits out the prime, it's the ith indexed prime. So there's a generic formula for this, which I wrote down after the dot dot dots. Let's see if I can show you this. So here's the generic ith summed polynomial. I don't know if I have another good name for this. They're like addend. How about a polynomial addend? That sounds pretty good. Or summand. Yeah, let's go with that. Polynomial summand. So for the ith, this is kind of cheating. I have to put in words here that pretty much you skip the x minus I factor. I didn't really know how to write that here because, if I is 1, then I would actually skip this factor right here. So I have to write in words, skip the x minus ith factor. And this is, I tried to explain it like this, x minus 1, x minus 2, x minus 3, dot, dot, dot. all the way up to x minus I minus 1, and then you skip over to x minus I plus 1. So you skip x minus I. That's how I tried to write it. And then you go all the way, continue all the way up on to n. All right, so that gives you zeros at all the integers except for the ith, or except when x equals I. Now I just have to make the value of that chunk, of this chunk right here. Oh, I think we had it as a blue chunk, right? I have to make the value of this blue chunk equal 1. So I have to multiply it by a scalar multiple, which is the green chunk, which you've seen before. And again, oh my goodness, I selected green, did I not? Okay, so at this green scalar multiple, make sure that the blue chunk, when evaluated at I, is divided by a particular number so that it equals 1. So I have I minus 1, I minus 2, I minus 3, all the way until the I, and then I skip to the I minus I plus I factor. So I'm skipping the I minus I factor, which would of course be 0, which would be extremely problematic. And then I continue from there all the way up until n. So the blue and green chunk together on the ith summand polynomial is going to be 1, so just the blue and green chunk, so I have to multiply by p sub I, which is the ith prime. So that's the generic formula for n primes, a polynomial that will pass through n primes for consecutive integers. So that's pretty good, don't you think? You asked for a polynomial that can pass through as many primes as you can, and I can do as many as you want. You give me a number and I can do one bigger than it, so take that. So of course I've got to finish off my polynomial going up to n, but you know what's going to go on. I have x minus 1 all the way up to x minus n minus 1, but I skip the x minus n factor, skip that one for the last guy, and then I do the same thing over here. I have n minus 1, n minus 2, and then over here I'm skipping the n minus n factor is skipped, because that would be dividing by 0, and I don't need to anyway because I've skipped it over here as well on the numerator. And then I just have to multiply by the last prime you asked me to give. And of course, every teacher that asks you to do this would of course give you n minus 1 primes, so just to one-up them, you give them n primes. So that's part 2 of my explanation. In part 3, I'm going to show how you can generalize this algorithm, I suppose. And so you can pass through any points. They can be decimals, irrationals, who cares? Pass through any points in 2D space, just so long as they're not vertically stacked. All right, we'll see you in a second, Mr. Brown.